Hello, hello, hello. Amir, how are you?
I'm good. How are you today?
I'm good, thank you, thank you. Hi, everyone. Today is another day. We have another video. It's one of the applications of derivative in calculus. It's an optimization problem, and Amir is going to help me to solve this problem, explain it to all of you. So Amir, let me explain this problem to you. Assume you have a material, the surface area of this material is 1200 square centimeter is given. And so let's say you're a contractor. You're trying to maximize, you want to make a box out of this material, let's say it's a cardboard or a metal, and you wanted to maximize the volume of this box.
Yes.
So the box that you're going to make out of this cardboard, let's say it has a base of a square, and also it has 4 sides, but it doesn't have a top. So you
Yes,
have
I can.
5, the box has 5 surfaces, the bottom, which is a
Yes.
square, and 4 sides, no top.
No top.
Yeah. So you're going to find basically the size of the base of this box and also the height of this box, such a way
Yes.
that the volume is maximum, and
Yes.
the amount of material you're going to use is 1200 square centimeter.
Yeah, it's predetermined. Yeah.
Exactly.
Yeah, that makes sense. Like, when you want to move out or, you want to put more stuff in the box, you want to maximize it. So it has a real life application, I believe.
Exactly.
So,
Yeah.
yeah, thanks for designing the problem. That's a good one. So let me just have a simple sketch of the box.
Yeah, that's going to help to illustrate the problem.
Let me. So, and we don't have any top, so I'm gonna just
the top is
highlight.
open.
Yeah, I'm just gonna highlight. That's front. So
yeah, we have 2 sides on the back and the sides, and then the bottom is also a square.
Correct.
That what we know, the bottom is
that's the
square.
side. So this one is
open.
Actually, let me. And the base is a square. So
yes,
I'm gonna call the length of the side of the base x and x.
Yeah. Okay.
And x is obviously greater than 0. And I'm gonna call the height of the box like lowercase h.
Okay.
So based on that, we have a prism with a square base, and the volume of that prism is V. I call it V volume.
Okay.
The area of the base, which is this one, the area of the base, x squared times the height.
Right.
So that's the definition of the volume of a prism.
So you have you define like 2 variables, x and h, and you define the volume in terms of x and h.
X and h.
And we're trying to maximize this volume.
Yeah, whenever we have, I think I also explained in the previous video that whenever we have like a maximization or minimization problem, an optimization problem, like in here, we better to find a function in terms of, one variable. That's like a rule of thumb we may consider. So our function is here is the volume of the prism. But as you can see, it's based on two variables. These two variables should be dependent on each other.
Right.
So that's why we need another equation to find one in terms of another. And the constraint for that in this problem is this number, the area of that cardboard or metal is given. So that's a good point. That's a clue. So we can use that. The area of the cardboard.
So you're saying that you have two variables here, but they're not independent. You can define using the constraint of the problem. You can define one of them in terms of the other.
Correct. X and H are dependent, and the cardboard area that we want to make this box out of that is this side 1, 2, 1 in back, and here 4 and 1 in bottom. So we have five sides because top is open. So let me see. Okay, 1,200 square centimeter is equal to the side underneath the base, which is x squared, the area of that, plus we have 4 sides around the box, which is 4 times x times h. Here it's h. So x, h. So yeah, this one.
Can you write? Maybe it's better to maybe under the first term, if you write base, and under the second term, maybe write.
Let me do this. Sure.
Sides.
Base, side, and we have 4 sides.
Right. And
yeah.
Obviously, you're assuming that there is no base. You're going to use all of that 1,200 square centimeter of material.
That's an assumption. Correct. So assumption.
No waste.
No. Correct. Material waste. So equation number 2 gives me, that dependency that I just mentioned between these two. So I'm gonna keep x in the function and just get rid of h. So I just obtain everything in terms of, let me do like this. 4xh is equal to 1,200 minus x squared. Then h is equal to 300 divided by x minus x divided by 4, if I'm not wrong.
You divide both sides by 4 times x.
Correct.
And we know that x is not 0, so there is no problem dividing by x.
That's correct. Because if x is 0, there is no box.
Yeah, that's correct.
So that's one of the constraints.
Yeah, and here you chose to find h in terms of x, and I think this is like an obvious choice because h is first degree, x is second degree, so it's like more involved if you wanted to find x in terms of h.
Exactly.
Yeah.
And so I call this one number 3. So I'm gonna put number 3 inside number 1. So based on 1 and 3, I get the volume in terms of x, which is x squared times
H.
300 divided by x minus, yes, x by 4. And that's, this one is h. As you can see, we have that function that I just explained at the beginning of the problem. We are looking for a function in terms of a variable, a physical variable that we have. In this case, is the size of the base, the size of one side of the base. So here, since we want to find the extremum of v, which is in this case the maximum, we have to take the derivative of v in terms of x. That's
Right.
the optimization problem. So we want to take the derivative of d over dx and make it equal to 0. So optimization problem. Let me just distribute x inside the brackets. So it's going to be 300 times x minus x cubed over 4. Correct?
Yes.
Okay, this one is easier to work with.
Yeah.
So I call this number 4.
And your goal is to find the x such a way v of x
Yes,
as maximum.
that's correct. This one is the goal, actually. So based on 4 and 5, equations 4 and 5, I'm going to take the derivative of this function. So it's going to be, I call it v prime is equal to 300 minus 3x squared over 4 equal to 0. I solve this in terms of x. It's going to be, let me like this. I multiply both sides by 4 over 3. So it's x squared times 1200 divided by 3, which is 400. And I'm just obtain the square root of both sides, which is 20. And since x is greater than 0 as one of our constraints, negative 20 is not answer.
Right. Yeah,
So,
because if
yeah,
a viewer wonders, this is a quadratic equation, why we got only one answer. The other answer is negative 20, which doesn't make sense to have a box with the size of negative 20.
yes.
So you made it clear at the beginning, x has to be greater than 0. So the other answer is not acceptable.
Yes. And okay, what are we going to do with this 20? So we want to put this 20 inside our volume function, correct?
Yes.
But we have to show that if this 20 is going to make it maximum or minimum. So I call this x as critical point. So this critical point, I'm gonna investigate if it's absolute maximum or minimum. The easier way is just looking at the derivative of v, which is this one. For values less than 20, if I put 20 in here, for example, 10, I'm going to get a positive value because like 300 minus 3 times 100 divided by 4 is going to be a positive number. So for x less than 20, v prime of 20, sorry, v prime of x is positive. And if I put x greater than 20, like 21, 22, 30 in here, I'm going to get a negative value because the second term is going to be larger than 300. So it's going to be negative. So for x greater than 20, I get as negative. And we know that.
Can you maybe draw a schematic
Yeah.
curve and show, what's going on here?
Yeah, we know that the derivative of a function is like a slope of that function,
Yes.
tangential to that x. So if I'm going to sketch, okay, before the r critical point, it is positive in here. So it's going to be like this one. Because in here, we have positive slope.
Right. So that curve is a curve, is like a schematic curve of v of x, for example.
Correct. Yes. Yes. Thanks for mentioning that. So yes, this is v of x.
And then that point, maybe
That's
just
the
indicate that
critical point. Yeah.
that's your 20, x
Correct.
equal 20.
Correct. Because the sign
maybe
of
show
the
it if you can. Maybe if you can show it on the horizontal axis. If you draw a horizontal axis and show 20 on that axis.
Okay.
Instead of writing.
Yeah.
Okay, so that 20 is, you're saying that you're investigating if this 20 at x equal 20, v of x is maximum or minimum.
Yeah, it's maximum. So it's absolute maximum in here.
Right.
So it is maximum. So v is maximum. It means if we put this 20 inside our v volume function, we get maximum of the function. We maximize the function. So that's the point of explaining these actually here. So I'm going to put x equals 20 inside our volume function. So for v of x equals 20, I get this one. I get 300 times 20
minus 20
cubed over 4.
by 4.
So it's going to be 6,000 minus 8,000. So it is 2,000, 4,000. Correct?
Yes, that's the volume, the maximum volume you can get. And h is, so you found the base, which is going to be 20 by 20 centimeter, and the height is going to be can you scroll up? You had the equation for the height. Okay, height. 300 divided by 20.
Yeah, I can write it down.
Minus,
just a second, please.
Okay. Yeah, that equation.
Yeah. So I go to the next page. So x equals 20. Then for h, I get 300 divided by 20 minus 20 divided by 4. So it's going to be 15 minus 5, 10.
10 centimeters.
Yes. So x is 20 centimeters, h is 10 centimeters. And if you make the cardboard by these dimensions, you get the maximum volume of 4,000 centimeter cube. So
Okay. Yeah, thank you.
sure.
Let me summarize what you did here. If you scroll up to the
Yeah,
first page, so you started by assigning variables to the base and height dimensions, h
correct,
for the base and I'm sorry, h for the height and x for the base.
correct.
And so because it's a cube, as
A
a result,
prism, yeah,
a prism, as a result, the volume is going to be x squared times h. And then, although we're seeing two variables here, these two variables are not independent. You can use the constraint in this problem, which is the
mm,
surface area of the material, to find one in terms of another. And you chose to find h in terms of x,
correct.
which is shown in the third equation, and you plug that into the first equation, the volume equation, and you find v in terms of x is a function in terms of x, and you're trying to maximize that function, which
Correct.
so you're using the derivative
Derivative. Yeah,
of the volume, as you showed in the fifth equation. And
correct.
so you solve that, and you found that x is equal to, x has to be 20.
Yes.
Then to make sure that this is the maximum, absolute maximum, not minimum, basically you look at uh, the the value of the derivative of the function for the values of x less than and greater than the critical point x equal 20.
Yes.
And you found that before x equal 20, the derivative is positive, meaning the slope is positive. And after that, the slope becomes negative. That's why at x equal 20, the volume becomes like the
Maximum.
largest
Yeah.
possible volume. And then you plug that number back into the equation that you had for h, and you found that h has to be 10 in this case.
Yeah.
And when you put these numbers into the function for the v, then
Yeah.
you can calculate the maximum volume, which is 4,000 cubic centimeter. And all of this is based on the assumption that there is no
Material waste.
material waste. So you're going to
Yeah.
use all that material. All right.
Correct.
Yeah. Thank you, Amir. I really appreciate your help. And,
Sure.
that was very clear explanation. And for the viewers, if you have any questions, please leave your questions in the comment section below this video. And till next video, bye, everyone. Bye, Amir.
Bye. Thank you. Bye.
Thank you.